Hi everyone, this is Dr. G. Amarendra Rao. In this session, we'll be discussing about one-dimensional steady-state heat conduction in hollow cylinders. Hollow cylinders are popularly used in many mechanical engineering applications like boiler tubes. These cylinders are so long that they can be considered as one-dimensional systems, which means that the length of the cylinder will be several meters, whereas the thickness of the cylinder is going to be few millimeters. Therefore, the radial dimension is going to be very small compared to the axial dimension as well as the angular dimension. Further, we would be waiting for so much of time that we reach steady state conditions, so that both 1D and steady state conditions are fulfilled. Here we pick up a hollow cylinder of inner diameter D1 shown by red color, outer diameter D2 shown by violet color, and length L normal to the screen. It's made up of a material of thermal conductivity K as shown over here. Then further, in order to have the heat transfer, we assume that the inner surface is maintained at some temperature T1, while the outer one is at some temperature T2, with T1 greater than T2. Mathematically speaking, at R is equal to R1, we have T is equal to T1. At R is equal to R2, we have T is equal to T2, with T1 greater than T2. Now we are intending to get the expressions for heat transfer rate and the temperature profile within the cylinder. And we can carry out the analysis by two popular methods. Method one is we can adopt the Fourier law, which for a radial system is given by Q is equal to minus Ka dt by dr. Or we can pick up the governing differential equation for cylinders will become d by dr or dt by dr is equal to 0. And by both these methods, we would get the similar expressions for both heat transfer rate and temperature distribution. And we can get to realize that the heat transfer rate is given by 2 pi kl log R2 by R1 times T1 minus T2. And temperature profile is going to be T1 minus T by T1 minus T2 is equal to natural logarithm R by R1 by natural logarithm of R2 by R1. We notice that on the left hand side T1 is highest and T2 is lowest, whereas on the right hand side R1 is lowest and R2 is highest. And both these equations will give us the required output of heat transfer rate and temperature distribution. Now we can carry out the analysis using the powerful electrical analogy, wherein the given hollow cylinder is replaced by an analog circuit with left side at T1 high potential, right side at T2 low potential, and the difference between T1 and T2 we call it as thermal potential responsible for the heat transfer. The heat transfer rate is hampered by thermal resistance RTH, and the Q is delta T by RTH as per the Ohm's law. And by looking at this equation and the conventional equation, we realize that thermal resistance is given by log R2 by R1 by 2 pi KL. And whenever length is not given, we take it as 1 meter. And since the cylinder has got various areas, inside area is A1, 2 pi R1L, outside area is A2, that is 2 pi R2L, we can always think about something called logarithmic mean area ALM. In this concept, the cylinder will be replaced by equivalent plane wall having an area of ALM normal to the direction of heat transfer. Remaining things are same material, same potential, same heat transfer rate. And the cylinder thickness is represented by LR, that we call it as radial thickness in meters. And we can write the expression for Q in a similar way as that of a plane wall. We know that in a plane wall, Q is given by Ka by L delta T. Analogous equation we write, only change is that A is replaced by ALM and L is replaced by LR. And by a simple mathematical procedure, we can show that this logarithmic mean area is given by a2 minus a1 by log a2 by a1, or a1 minus a2 by log a1 by a2. Both the equations are perfectly correct. If you use the first part of the equation, a2 is greater than a1, so numerator is positive, and a2 is greater than a1, so a2 by a1 is greater than 1. Log of anything greater than 1 is positive, so positive by positive you get positive mean area. If you use the second part of the equation, a1 is less than a2, so a1 minus a2 is negative, and a1 by a2 is less than 1. Log of anything less than 1 is negative, so negative by negative is positive. Again we are comfortable. So you can say that one area minus other area by log of first area by second area. Then we can always show that log mean area will be more than a1 less than a2. Then LR, I was telling, is R2 minus R1 is the radial thickness. So this log mean area concept enables us to write the expression for heat transfer rate analogous to that of a plane wall. Then we can always think about the concept of log mean radius, RLM. So in this concept, the hollow cylinder with different radii will be replaced by a mathematical solid cylinder having the radius of RLM in a way such that everything is same. This is the mathematical cylinder having a radius of RLM. Then we can write ALM, log mean area, as 2 pi RLML, where RLM is simply R2 minus R1 by log R2 by R1, or R1 minus R2 by log R1 by R2. And we can always show that R1 is going to be less than RLM, which is going to be less than R2. So it's going to be the mean of R1 and R2. Then we can always carry out the analysis by using governing differential equation, which can be obtained from the scratch from the fundamentals, wherein we consider a cylindrical strip at any radius r having thickness dr. Then del qr is the rate of energy coming in, and del qr plus dr is the rate of energy going out. And for this strip to be in steady state condition, energy coming in should be same as energy going out, the energy balance equation. And energy coming in can be found using Fourier law. Energy going out can be written in terms of energy coming in using Taylor series. And when we supplement both these equations over here, we are going to get the necessary governing differential equation, which can be integrated 2 times with appropriate boundary conditions to get the temperature distribution followed by the heat transfer rate. And GDE as well can be obtained by simplifying the general heat conduction equation in cylindrical coordinate system, wherein temperature is a function of r, theta, z and tau, where r is the radial coordinate, theta is the angular coordinate, z is the axial coordinate and tau is the time. And we are going to derive this equation in the forthcoming sessions that cover general heat conduction equation in a cylindrical system in a material of isotropic and homogeneous conditions is given by 1 by r del r or del t by del r plus 1 by r square del square t by del theta square plus del square t by del z square plus q dot by k is equal to 1 by alpha del t by del tau, wherein the first term accounts for radial heat conduction, second term takes care of angular heat conduction, third term accounts for axial heat conduction, fourth term is internal heat generation. All of them together we have right hand side, that is unsteady term. And we can always simplify this equation by incorporating some suitable assumptions. We can say no heat generation, fourth term vanishes, we'll be getting an equation named after Fourier. Then we can say steady state heat transfer, RHS is 0, we get the Poisson's equation. Then we can combine both these conditions, no heat generation, steady state, we get first 3 terms is equal to 0, there's a Laplace equation. Then we can have similar such assumptions, but the simplest possible is that one-dimensional steady state, no heat generation. That temperature is a function of R alone. It does not vary with theta. with jet, with time, and absolutely nothing is there inside to generate the heat. Then first term is equal to 0. Since temperature is a function of R alone, del can be replaced by d. d by dr or dt by dr is equal to 0. This is same as the governing differential equation, which is obtained from the basics. And this equation can be integrated 2 times to get the temperature distribution followed by the heat transfer rate. These are all some of the important concepts related to hollow cylinders. Now let's try to pick up some numericals. First one is a very general problem involving all the calculations. That a stainless steel cylinder K is equal to 16.5 watts per meter Kelvin of inner diameter 18 centimeters, outer diameter 22 centimeters, and length 3.5 meters has its inner surface at 85 degrees centigrade and outer surface at 25 degrees centigrade. Then find number 1 the radial heat transfer rate in kilowatts, number 2 thermal resistance in degrees centigrade per watt, number 3 temperature in degrees centigrade at R is equal to 10.2 centimeters, number 4 radius in centimeters where the temperature would be 50 degrees centigrade, number 5 mean radius of the cylinder in centimeters, and last one mean area of the cylinder in meters square. And if you jot down the data, for stainless steel K is 16.5 already given. Then we have inner radius 9 centimeters, the diameter by 2 by 100, it's going to be 0.09 meters. Outer radius is outer diameter by 2 is 11 centimeters divided by 100, 0.11 meters. Length is 3.5 meters. And inner surface temperature 85, outer surface temperature 25. Take the difference, is going to be 60. There is a thermal potential, and this diagram illustrates the entire data that's available to us. Then we have the formula for Q, it is 2 pi KL by log R2 by R1 into delta T. And if you supplement the entire data over here, we are going to get Q as 1,08,492.3588 watts. If we divide by 1000, 108.49 kilowatts. Then also we can write Q as delta T by RTH. Q is available, delta T is available. You can find RTH as delta T by Q, which is going to be 5.72 into 10 power minus 4 degrees centigrade per watt. Then we can find temperature at the given location of 10.2 centimeters. It's 0.102 meters. By using the formula of temperature distribution. So T1, T2 are given, R1, R2 are given, R is given, you are trying to find T, which is going to be 47.57 degrees centigrade. And we would like to look at the place where temperature is 50 degrees centigrade. Same equation, we have to find R, T is given, which is going to be 10.117 centimeters. Then RLM as per the formula is R2 minus R1 by log R2 by R1. And if you calculate, it's going to be 0.0996 meters. Into 100, it's going to be 9.96 centimeters. That's the mean radius. And mean area is A2 minus A1 by log A2 by A1. Or A1 minus A2 by log A1 by A2. R2 by RLML. All of them are okay. Since RLM is available, this formula would be more effective, and if you substitute for RLM, L is given, it's going to be 2.19 square meters. So this is a general problem involving all the basic calculations. And next problem is one-step problem, wherein we have an aluminum cylinder of inner diameter 12 centimeters, conducts 385 kilowatts of heat per unit length across a thermal potential of 45 degrees centigrade. Find the thickness of the cylinder in millimeters. For aluminum, we can take K as 201. So if we jot down the data, R1 is 6 centimeters, 0.06 meters. Heat transfer rate per unit length, Q by L is given 385 kilowatts per meter. Multiply by 1000, 3,85,000 watts per meter. Potential is 45 degrees centigrade, K is 201. And if you substitute this data in the standard equation, Q by L is 2 pi K log R2 by R1 delta T. Only unknown is R2, that can be worked out from this equation as 0.0695 meters. Thickness is R2 minus R1, so 0.0695 minus 0.06, it's going to be 9.954 10 power minus 3 meters. If you multiply by 1000, you are going to get as almost 10 mm, that is 9.954 mm. Then we look at another problem. A hollow cylinder of ID 14 centimeters, OD 16.5 centimeters, length 1.8 meters, conducts 700 kilowatts of heat across a thermal potential of 52 degrees centigrade. Find the thermal conductivity of the cylinder material. Also identify the material from the following options: A. Mild steel, B. Aluminium, C. Copper, D. Cast iron. Again here only one unknown, because R1 is given 7 centimeters, 0.07. R2 is given 8.25 centimeters, 0.0825. Q is 700 kilowatts, 700,000 watts. Length is 1.8 meters, delta T 52 degrees centigrade. And Q is given by this equation, 2 pi KL by log R2 by R1 delta T. And if you work out for K, it's going to be Q times log R2 by R1 by 2 pi L delta T. And if you substitute the entire data, K is going to be 195.56 watts per meter Kelvin, very close to 200. Therefore, the material is going to be aluminium. So these are some of the problems which may be useful to you in any of the examinations. So in the next session, we'll be talking about hollow spheres. Till that time, have a nice time.